High above Earth's cerulean swirl, an astronaut glides from the airlock of the International Space Station. She lets go of the handrail, and for a heartbeat, appears perfectly still, a lone figure, afloat in velvet silence. Yet without firing a single thruster, she is hurtling around the planet at 7.7 kilometers per second, surfing a curve of space-time that never ends. Motion, it seems, does not wait for engines. It is stitched into the fabric beneath her gloves. The illusion of rest has always tempted us. Set a teacup on the table, and it stays put. Step off a moving boat, and the pier feels solid, dependable. But history whispers a different story. Galileo watched lanterns top Tuscan ships and realized the deck was no privileged stage. Newton chiseled that insight into law, declaring that a body in motion will carry on no coaxing. No cause unless another body intervenes. Inertia, he called it. The quiet sovereignty of straight-line movement. Yet straight lines are rarer than we imagine. The deck rolls with the tides of Earth's spin. The planet loops the sun. Sun pirouettes around the Milky Way. The galaxy itself is dragged by unseen currents toward the great cosmic cities of Virgo and Laniakea. We dwell on a spiral staircase of velocities, each step hidden under the carpet of daily life. Lift your gaze farther still, and a grander restlessness appears. Edwin Hubble noticed galaxies slipping away from one another like glowing embers cast into the dark. Today we map that flight in exquisite detail, and the data reveal a deeper puzzle. The cosmic expansion is speeding up, as though a subtle hand, dark energy we name it, were tugging on every meter of space. In such a universe, what does at rest even mean? Can inertia coexist with a stage that stretches beneath the actor's feet? Some thinkers, like Ernst Mach, wondered whether motion is defined only by the whole. Perhaps the mass of distant galaxies whispers to every atom, telling it what counts as straight, what counts as still. Einstein absorbed that hint and found that free fall is not the absence of gravity, but the purest expression of inertia. Objects following the natural curves of space-time itself? On this view, the astronaut, the teacup, and a drifting comet share the same calling. To trace geodesics lines so honest, they need no push. And yet, an unsettled note lingers. Space is expanding. If the very ruler we measure motion with is changing length, then inertia is no longer merely a law of persistence. It becomes a conversation between matter and metric, between the stubbornness of mass and the pliability of the cosmos. That is the journey before us. We will step from Newton's quiet revolution to Einstein's soaring geometry, from the whispered pull of dark energy to the fate of voyagers coasting into an ever lonelier sky. Along the way, we will ask a deceptively simple question. Why does anything move at all, and why does nothing, not even stillness, ever truly last? Imagine you are sealed below deck on a calm-bellied galleon. No porthole, no roll of horizon. Only the lantern's meek glow and the creak of timbers. A glass of wine rests on the table. Beside it, a brass ball lies ready on a gently sloped wooden plank. You release the ball, rolls, slows, and settles. You tilt the plank again. And again the ball obeys exactly as it would in any motionless cellar ashore. Galileo loved this cabin thought experiment, for it whispered a quiet heresy. The ship may be slicing through waves at 10 knots, yet the laws inside neither feel nor care. Motion, he intuited, is not something you carry like luggage. It is a condition that, once acquired, demands no further tribute. The candle's flame stands upright not because the vessel is truly still, but because every particle of flame, glass, and air shares the ship's invisible glide. From this humblest of stages, the cramped hold of a Renaissance vessel emerged a revolution. If experiments cannot reveal steady motion, then rest and uniform travel must be twins wearing different costumes. The sea, Galileo realized, exposed a flaw in centuries of Aristotelian certainty. Perhaps nature does not crave stillness at all. Perhaps left unbothered, motion would simply be a silent companion, needing no cause, awaiting only recognition. 4 decades later, in a drafty Cambridge study, Isaac Newton set quill to parchment and gave Galileo's intuition the weight of law. First principle, every body perseveres in its state of rest, or of uniform motion in a straight line, unless compelled to change that state by forces impressed upon it. 20 Welsh words in Latin dress, yet they dethroned to millennia of common sense. Aristotle had taught that a cart rumbles only while the horse strains, that an arrow keeps flying because the air itself continues to push it along. Newton answered with radical economy. Remove friction, silence the wind, and the cart will glide forever. Strip the arrow of drag, and it will wander endlessly among the stars. Force, he said, is not the sustainer of motion, but the author of change in motion. An editor's pen, not the page beneath. To his peers, the claim felt perilous. After all, earthly experience teems with slowing wheels and falling arrows. But Newton had seen deeper. Those stoppages arise from hidden pushes. Gravel under a wheel, air against a shaft. Not from any natural longing for rest. Between pushes, the universe is content to let momentum stream onward, pristine and unburdened. Thus, inertia became more than a property. It became a promise. It states that the cosmos keeps immaculate bookkeeping. Whatever straight-line motion an object possesses, it owns outright, untaxed by time. Only an external nudge, a force, can renegotiate that ledger. In this single stroke, Newton transformed motion from fleeting gift into enduring right, granted to every planet, pebble, and drifting human heart. On a summer evening in Woolsthorpe, Newton filled a wooden pail, hung it by a rope, and set it spinning. At first, the water's surface stayed calm, while the bucket blurred around it. Then, as the liquid caught the rotation, its surface climbed the walls, forming a quiet parabola. When Newton halted the bucket, the water continued to whirl, the curved surface lingering until friction bled the motion away. To Newton, this modest experiment spoke volumes. The creeping rise of water could not be blamed on the bucket's boards. They had briefly rested while the water still spun, so the cause, he reasoned, must be rotation with respect to something else, something unseen yet universal. He called it absolute space, an invisible scaffold against which true motion and true stillness are measured. This idea granted inertia a silent referee. Stone tied to a sling tugs outward not because it senses the twine, but because its straight-line instinct clashes with a forced circle around that immaterial stage. Even if every star vanished from the sky, Newton believed the stone would still feel the pull. Absolute space needed no landmarks. Yet a seed of doubt lay dormant in the bucket's swirl. If forces arise only from motion relative to this undefined backdrop, might that backdrop itself be nothing more than the distant mass of the universe? Einstein would later wonder. Mach before him would prod. But for a century and more, Newton's unseen lattice of space remained the quiet canvas upon which all celestial choreography was drawn. Paris, 1851. In the vaulted dome of the Pantheon. Leon Foucault releases a 28-kilogram brass bob suspended on a 67-meter wire. With each languid swing, the pendulum traces a line in sand, and hour by hour that line slowly rotates beneath the tourist's feet. The floor, the pillars, the city itself are turning. The pendulum is merely keeping faith with inertia, pointing toward a frame beyond the rattling carriages of the Champs-Élysées. Half a world away, trade winds curve and hurricanes spin, sculpted by the same invisible hand. The Coriolis force no force at all, merely inertia misread from a rotating deck, twists air and sea into vast spirals. Stand in the eye of a cyclone, and you feel nothing push you sideways. Yet the storm's arms curl because Earth pirouettes beneath them. These phenomena reveal motion without a single mile walked. They show that to detect rotation you need only watch how inertia expresses itself. A pendulum that refuses to follow the floor. Water that heaps against a bucket's rim, clouds that trace planetary whirls. No anchor is necessary, no celestial compass. Only the steadfast straightness objects cling to unless compelled. Such experiments whisper a radical message. Inertial frames are not bestowed by gilded labels like at rest or in motion. They emerge from relationships between swinging pendulum and turning earth, between spiraling storm and spinning globe. The stage feels less like Newton's absolute void and more like a dialogue with the cosmos itself. A dialogue that will grow louder when Mach and Einstein ask whether the distant stars might be answering back. By the late 1800s, physics had grown almost smug. Newton's mechanics charted planets with clockmaker grace. Maxwell's equations revealed light as a trembling electromagnetic wave. Waves everyone knew need a medium: water for ripples, air for sound. So scientists conjured an all-pervading luminiferous ether, an intangible sea through which light must sail. Surely if Earth coasted through that sea, a sensitive instrument could feel the headwind. Enter Albert Michelson and Edward Morley. In a quiet Cleveland basement, they floated an interferometer on a pool of mercury, splitting a beam of light into two perpendicular paths. If ether existed, turning the apparatus should stretch one light path, compress the other, and shift the interference fringes like ripples in a pond. They waited. The fringes held fast, no drift, no sigh of cosmic breeze. They turned the granite block again, and again silence. The null result rang louder than any positive finding. Either Earth always sits uniquely still in the ether, an implausible cosmic vanity, or the ether itself is a fiction. More unsettling, the speed of light appeared steadfast, immune to the motion of both source and observer. Here, inertia met something stranger than frictionless ice, a signal that refused to add or subtract velocities. A law unwilling to bend for common sense. The cracks spread quickly. If light needs no medium and no preferred frame, perhaps no such frame exists at all. Into that widening fissure, a young patent clerk named Einstein would step. Armed with the audacious idea that the straightest possible line in the universe may be drawn not through space alone, but through space-time itself. We have followed inertia from Galileo's hidden cabin to Newton's spinning bucket, from Foucault's solemn pendulum to Michelson's stubborn light. Each experiment has pulled another rug from beneath the notion of an absolute backdrop. Motion, we have learned, is not a privilege granted by a cosmic stagehand. It is the native state of things. And stillness, more often than not, is merely motion we share. Yet questions gather like clouds at twilight. If no lantern marks an ultimate rest frame, what fixes the line that inertia calls straight? Why does a rotating bucket know it is spinning, even in an empty room? And could that knowledge, as Ernst Mach dared suggest, be whispered to it by the far-flung galaxies themselves? Might inertia be a handshake with the total mass of the universe? A silent referendum in which every star has a vote? These riddles press us to widen our lens. In the next chapter, we will leave Newton's absolute space behind and enter a realm where frames float anchorless, where the very geometry of space-time decides what counts as a geodesic path. We will weigh Mach's provocative principle against the evidence of rotating heavens. Watch Einstein fold gravity into inertia, and glimpse how the cosmos itself may set the rules for every apple's fall and every satellite's glide. It's so let the bucket's water settle and the pendulum's sand run smooth. Ahead lies a deeper mystery. If motion is free, yet reference is relative, who or what draws the grid that guides the stars?